Hello all. In this video, I'm going to explain red-black tree. Red-black tree is also a self-balanced binary search tree. So, binary search tree means left subtree elements are less than root, all right subtree elements are greater than root. And every node is either black or red. We'll assign color to each and every node. Either every node is either black or red, and always the root is black. So always the root node is black. So we'll assign black to root node. And all leaf nodes, leaf which is nil, it means that, for example, all these are nodes in binary search tree. There is no left subtree, there is no left children for this node. It means that nil node. There is no right child means nil. For this node also, there is no left child, there is no right child. For this node, this is left child of this node. There is no right child, means it is nil. So leaf which is nil is also black. So if we want, we can assign numbers also: 15, 10, 25, 5. See, for 10, left child is 5. There is no right child. It means that it is nil node. So all leaf which is nil nodes are black and root is also black. And one more. If parent is black, child can be black or red. Okay. If parent is black, child can be red or child can be black. Any color we can assign. But if parent is red, child should be black. Child cannot be red. No two adjacent can be red. No two adjacent can be red. So this is not red-black tree property. It is violating the property of red-black tree. And one more condition, one more property of red-black tree. Every path from node to any of its descendant nil node, the number of black nodes should be same. So I'll tell you with example. Any node, not only from root. For example, I'm going to traverse from this node. I'm going to assign color black, red, like a black. So if we traverse from 10 to this nil node is also black, black, black. If we traverse from 10 to this nil node, the number of blacks are 1 and 2. If we traverse from 10 to this nil node, the number of blacks are 1 and 2. If we traverse from 10 to this nil node, the number of blacks are 1 and 2. So like this, the number of blacks should be same. We'll take one more example. If we traverse from 15 to this nil node, the number of blacks are 1, 2 and 3. If we traverse from this to this nil node, 1, 2 and 3. If we traverse from this nil node, this root node to nil node, the number of blacks are 3, the number of blacks are 3. So every path from node to any of its descendant nil node, the number of blacks should be same. See, these are the properties of a red-black tree. It is a self-balancing binary search tree. Every node is either black or red. Root is always black. Every leaf which is nil is also black. And if node is red, then its children are black. No two adjacent can be red. And one more. Every path from a node to any of its descendant nil has same number of black nodes. These are red-black tree properties. So I'll show you few examples. We'll check it once. Is it red-black tree or not? 10 is root. Root always black. So here the root is red. Means it is not red-black tree. And next, root is black. And anyway, all nil nodes are black only. And next, See, all these are blacks, and if you traverse from any node to any of its descendant nil node, these are nil nodes. So all these are nil nodes. So if it travels from any node to its descendant nil node, the number of blacks are same. So it is a red black tree only. And we'll take one more example. See, root is black, child. If root is black, parent is black, child can be black or red. If parent is black, child can be black. Both childs can be black. Now, now the parent is red. Child cannot be red. Child should be black. So it is red-red conflict. It is not a red-black tree. And one more. If it travels from node to any of its descendant nil node. So all these are nil nodes. If it travels from here to here, the number of blacks are 1, 2 and 3. If it travels from this root node to this nil node, 1, 2, only 2 blacks. So it is not red black tree.